Hello, welcome to this first video lecture for the course of Elective in Robotics and Control Problems in Robotics, the module of Locomotion and Haptic interfaces. Today we will present the first of the two CyberWalk platforms that we have been talking in the introductory part of the course. It will be the so-called ball array platform. We will go through the slides which will present what is the problem in terms of motion control that we would like to achieve. Then we will describe the hardware of the device that has been built. It's a small-scale platform. And then we will see, after introducing a kinematic model of how the command will give motion to the user standing on top of this platform, we will see how these commands can be designed as a combination of feedback and feed-forward terms in such a way that we achieve the control objective. So, the ball array or bearing platform is the first of the two platforms that you can see on the left and on the right. It's also called the Magic Carpet. It was the first one that was developed within the CyberWalk European project. And it was built only at a small scale size. The reason for this is because we have several technical difficulties in extending the design. But it's interesting because it can be considered as a non-holonomic mobile platform with some nice association with what you may know about the kinematics and the control of wheel mobile robots. The other array is the two-dimensional belt array made up of treadmills mounted on a chain, and you can see on the right the one-dimensional treadmill that we used for tuning the control law, and below the final full-scale platform, which at the time of this project was the largest actually locomotion platform built in the world. So on the left, so in this lecture we will concentrate on the ball array or bearing platform. And you can see below a small humanoid placed on top of this magic carpet of balls. And on top we have a simulation environment that we developed. We placed a humanoid on top of this platform. Now don't take into account the actual size of this. So this platform will rotate around the center. And the blue part is representing the belt of this platform. And in between there are also the balls, but we didn't model this in the kinematic point of view. So when you see the two red wheels rotating, it means that the platform is shifting along the main direction. So the final goal that we would like to achieve, this is an introductory video, is bringing the user, which is now close to the boundary of the platform, back to the center. In this case, the user will not move, so, it will move indeed, there's a specific motion, but you see that the platform is rearranging its orientation and motion in the linear direction in such a way that the user is brought back to the center. We'll see how this is achieved. Okay, so let's move on and start with what are the control specifications of our problem. So essentially, as we said, we would like to keep the walker as close as possible, but really not really at the center, but close to the center of the platform. Why close? because in fact we have some, say, boundary before the user would fall out of the platform. So we could afford to stay not exactly at the center, depending on the size, of course, of the platform. So we have to take into account the platform dimension in order to specify what do we mean by close. In principle, we would like to bring the walker at the center. And the other thing which is very important in this problem is that we don't really care about which orientation the walker has, independently of the fact that it's an intentional orientation that the walker achieves by rotating on place or walking by changing direction, or if it's the platform itself that is reorienting a standing walker or a walker while it is moving. Why the orientation is not relevant? Well, because we are using those locomotion platform with a user which is immersed in a virtual reality. So the actual orientation of the user is not relevant as long as the orientation in the virtual world is the one that the walker desires. So this depends really on how the head-mounted display is used by the user. So while doing this, we could do this pretty much easily if we didn't have some constraints. And the constraints are coming exactly from perceptual feelings that the user has while standing or moving on a moving platform. So we would like, by and large, to give control input which are sufficiently smooth so that the user is not affected by the fact that the platform is moving. So this is especially true when the user starts walking and stops walking, because the acceleration in these phases is pretty much large, and we would like to compensate essentially the intentional motion without affecting the balance of the user, at least. The only aspect, the other important aspect of this control problem is that we have only a measurement of the position, the body position of the walker in a sense. For instance, we may use a visual camera mounted on top of the platform, and this is in fact what we did for the MotionControl platform, and we will use this in order to localize where the user is. And possibly from that information we can also extract the walker orientation, so how his trunk is oriented, although you may understand that sometimes there are situations in which we are not walking in the direction of our trunk. So typically we may walk on the side, like I'm doing now on my wheelchair, or just walk in one direction while looking in diagonal. So the handling of the orientation is quite critical. But this information may be useful. In principle, we could extract this information or orientation, but eventually we may also not use it for control purposes. The other aspect is that the walker has its idea of how to move in the virtual world. So we have no a priori information about which will be the direction of motion of the user. So in particular, which velocity or which acceleration the walker has will possess in the next future. So this is clearly unknown. There's no way of sensing this information, but if we could predict somehow which would be the next move of the user, then we could anticipate in some sense this displacement and start already compensating the motion of the platform in such a way that we keep the walker close to the platform center, as we said. Last but not least, it is very important, although this is not a control problem, but it's really important to synchronize the control commands which will move the platform with the part which is more related to the visualization of the virtual world that the user is living in. Because in fact, if the user is standing still, not changing his head, so he would like to see a perfectly still scene with his eyes, with the head-mounted display, and if in between the platform is bringing back the user to the center of the workspace, then of course this motion should completely be cancelled in the visualization. And this is in fact something quite relevant. So there's the need of coordinating and also having the same timestamps of the commands that goes to the platform together with the commands that goes to the visualizing part of the system. Okay, so let's start looking at the hardware. So how was this platform designed, the ball array platform? I already mentioned in my introductory lecture that this idea was not completely new, although there are small variation and this small variation gave rise to different patterns of this idea. There was another group in Japan that designed a similar ball array platform. But let's see how we did it in this project. So the platform is constituted by basically a treadmill, and on the top figure you can see the green belt that will move back and forth along the direction of the treadmill. And this treadmill is mounted on a turntable, so it can rotate. So the main axis of the treadmill would rotate. Now this rotation, however, is not the one that reaches the user, which will stand on top of the platform. In between, there is an array of small balls arranged. Now you can see the balls completely free, but in fact they are arranged in a grid so that they remain in place, and the contact between the sole, the normal sole of the normal shoes that the user is wearing, and the treadmill occurs through the contact of this array of small balls. So in the bottom figure you can see below the belt of the treadmill, so the green part in the previous figure, one of the many small balls that are sitting on top. This is what we call the magic carpet, and they are encapsulated in a grid. So you can see the light gray part, right and left, are part of the grid sustaining the balls. The balls are free to roll here, and in fact you see that there is also some small clearance, so that the assembly of this is rather easier than if the balls were fixed inside this hole. And on top of it you see the slightly deformed shoe sole that is in contact with one, in fact with many of these small balls. Now, as the force diagram shows, when the treadmill is moving at the bottom, so it's applying the force going from right to the left to the rolling ball may be in contact, in practice it is immediately in contact with the side of the grid, but starts rotating. And on the other side of the ball, the equivalent force is applied in the opposite direction to the shoe sole. So in this diagram of forces, of course, you would like to transmit, to generate a force between the ball and the treadmill because of the high friction. So that as soon as you move the belt, the ball will start rolling, and because of high friction, this roll of the ball below the shoe sole will let shift the feet of the user on the opposite side. On the other hand, the ball is in contact with the grid, and it generates a friction force, which can be decomposed in a normal force and in a tangential force. And we would like that friction at this contact should be the least possible, so that the ball is not opposed by this contact in its pure rolling. And this physical consideration, guide us in the choice of the material of the belt, the material of the grid, the size of the ball itself, and so on and so on. Of course, we cannot make. We decided, in fact, in the project, not to make any restriction on the shoes that the user is wearing. So you can start working on top of this platform, even if it's small size, with regular garments. So, as I said, we started with a small size design. Eventually, we end up with this hexagon that you can see on top left, which is inscribed in an outer circle of 80 centimeters of size, and the inner circle is about 68 centimeters of size. There's a huge number of balls that have been placed, more than 4,000 balls, each of a diameter of 8 millimeters, so that when you place your foot on this ball array, you have a feeling of a uniform contact. There's also small gaps between one ball and the other. This is pretty much clear in the bottom figure. And as you see, they are placed in these holes, but without any, let's say, restriction to their mobility. Before making this choice, which was, in fact, using inox steel balls and a so-called acetal plate. The white plate is made by polyoxymethylene, which is a thermoplastic with high stiffness and quite low friction. We made some intermediate study. For instance, there are available on the market polyethylene stripes like the one that you see in the top figure in the center, but they were too delicate to be used. So eventually we made this choice, and it is interesting to know that the coefficient friction between the ball in contact with the side of the acetal plate used for the grid has a relatively low value of 0.3. You will see that a larger value can be considered for other type of contacts. So this was the magic carpet, and this magic carpet is anchored on top, placed on top of a treadmill. So we have a linear treadmill, which, because of the small size, we took a commercial product which has a length of 1.1 meter and 0.8 meter of width. By the way, this is also close to what is considered to be the best ratio between length and width of this type of treadmills. And this treadmills goes in one or the other direction, so it's bidirectional, and it's driven by an AC motor with 3 phases. Lenze is the brand, which can provide up to 2 Newton meter of maximum torque. And on the motor axis output, there is a reduction element which reduces speed from the motor to the load size by a factor of 20, increasing by the same factor the transmitted torque. So with this, the linear treadmill, using this motor, can reach up to 2 meters per second of linear speed and up to 5 meters per second square of linear acceleration. So the treadmill is self-standing. Of course, it can be mounted properly, and we will see the full assembly of the platform in the next slide. But there are other choices to be made. So the belt, the green part, the part which slides when the motor is on, is made of PVC, so polyvinyl chloride, which is, by the way, the world's third widely produced synthetic plastic polymer. The thickness is 5 millimeters, and the contact between the ball of the magic carpet, which are on top of the treadmill, and this material used for the belt has a larger coefficient, more than 0.7, so larger than the previous case. In fact, we would like that any linear motion of the belt moved by the lens motor will be transformed into a pure rolling, exactly the same amount of rolling, so without slippage of the balls, and in this way also transfer to the user, which is standing on top of it. Now, the last component of this assembly is the turntable. So the treadmill is mounted on a rotating platform, which is driven by the same type of motor. The only difference, it has a larger ratio. So one rotation of the motor is equal to, let's say 64 rotation of the motor is equal to one rotation of the load, and therefore the amplification of torque is even larger. And this transmission ratio is given by the gears on the output of the motor, plus the fact that the motor is placed offset of the center of rotation, and angular motion is transmitted through a toothed belt. So the total transmission ratio is 1 to 64. With this arrangement, so the same type of motor, as I said, we could reach 2 radians per second of angular speed and 20 radians per second square of angular acceleration. Now, once we place all these things together, so the magic carpet, the turntable, and any other component that needs to move with respect to the fixed ground, so the total weight of the moving parts in rotation is about 200 kilograms. And, but this system is able to sustain, in fact, the weight of a relatively heavy person up to 100 kilograms. So there's a 1 to 2 payload ratio in this sense. So here in this next slide, we can see how the different parts come together. You see on the right top side the final setting. On top of the platform of this CyberCarpet platform, there is a wheeled, actually a tracked vehicle that we can teleoperate, which will mimic the motion of a user that moves on top in an unpredictable way. So, as I was saying, you can see the assembly on the left-hand side. There's a supporting part, a supporting structure, which is rigid enough not to introduce vibration. Then, coming from the bottom, you can see the motor 14 mounted on the side, so mounted on the frame with its axis connected to a belt, which will engage with a toothed wheel, number 9, in order to move the second supporting part, number 10, which holds also electronics, and of course the treadmill with its own motor. So one motor is not sustained, not in motion, so it's the motor that lets the turntable rotate, and the second motor is next to the treadmill, and of course needs to be moved together with the treadmill itself. So there will be an engagement. There will be a problem of transmitting cables from one side, from the top side to the bottom side, but this has all been solved. On top of this, you see the acetal plate with the grid where the more than 4,000 balls are placed. The two servo drives are the same. They have a power of 0.8 kilowatts. And now we will see a small video to understand the size of everything with respect to a human, and also some preliminary experiments. Okay, so here you see on top of the small size platform, in the front line you see the logos of the various contributors, including the Technical University of Munich, the ATH of Zurich, and in this particular case also contribution of our Sapienza University of Rome. Martin Schweiger was a PhD student at the time of the Technical University of Munich, and is standing and walking on top of this prototype. Now, what we will see in these two videos, you will hear also some sound, and the sound corresponds not only to the voices of the people sitting and watching this first experiment, but also to the noise of the motor moving below the platform and the treadmill. So, but in these cases there was no platform control. I mean, just to make a test, we provide commands to the motors, the platform moves essentially in one direction without changing orientation, and the walker adapts his speed accordingly. So in the first video, Martin Schweiger is walking while the treadmill is having a slow speed. And you can see that, in fact, he's walking, but he's standing on place. So the idea is that the motion, I mean, if the steps were intentional, the treadmill below would have moved in the opposite direction in such a way to keep, to provide an opposite velocity to the user, which would result in no motion. So the center of mass, in a sense, of the user remains at the center of the platform. Now, the second video is another experiment, and it's also the cause why we decided that it would have been hard to extend this to a full-size platform. But in any event, you will see that this works pretty much in a nice way, even at higher speed. So in this experiment, we start with 0 speed and then increase to a maximum at about 1.4 meters per second, which is the speed that you reach with walking considerably sustained. Something happens. So pay attention to the plate, to the white plate, and to the ball arrays. So the treadmill starts slowly, so in order to stay in place, slow, small steps are being done by Martin. And now we increase When we increase the speed, you may hear the sound in the background. And the frequency of steps increases. It increases also a little bit the size of the gates. But now something happens. In order to walk at this speed, large forces are being exerted on the balls, and they tend up to jump out of their location. And of course, this would be a critical issue. Indeed, we could have designed a supporting plate, a grid in which the balls remain always in place, but we would have increased the friction, and so we would have reduced the transmission of forces from the turntable and the treadmill to the soles of the walking user. So, with this in mind, let's see how we can describe what's going on. What is the relationship between the motion that we would impose as a reaction to the location of the user on top of this platform, so that the relation between the command that we impose through the actuators, in particular the linear and angular velocity that we gave to this to the turntable and to the treadmill, into a motion of the user standing on top of this platform. So we start with the overall system architecture, and we have here an overhead vision system, so a simple camera. We use the camera. In fact, you will see later on that we made a mock-up of a view of a human, so a picture of a human seen from above, and we mounted this mock-up on top of the tracked vehicle, so to make things more similar to the reality, but of course this is an abstraction. We do some image processing from where the walker position and orientation on the platform is being extracted. At the same time, we have low-level servo, which produces torques. In fact, we assume that there are low-level controllers that receive reference in terms of kinematic commands, so either speed or acceleration, and provide the right torque in order to implement those desired reference value. We have sensors from encoders that characterize, for instance, the angle theta of the treadmill, which is below the ball of arrays, the array of balls. All this information converge to the platform controller, which generates linear and angular motion commands. And we can imagine that we provide velocity inputs to the system or acceleration inputs to the system. We will see this at the end of this presentation. Everything should be coordinated with the virtual reality visualization. So, as I said before, if we move the platform in order to bring back the user to the center, this part of the user motion in the absolute reference frame should not contribute to the change of view in the visualization. Indeed, on the other hand, whatever change of head position and orientation of the user, intentional change, and also of its body, indeed, should be mapped into the visualization. Since in general we have a combination of both, so the user is moving his body, so it's walking, it's changing its head orientation, while the platform is trying to compensate this motion. So all them should be properly filtered and combined and synchronized in order that the visualization remains as with the highest fidelity as possible. Okay, so let's start by now with writing some equation. We will start first considering that the worker is just standing still on top of this ball array platform. Okay, so we have here the equation which describes the kinematic model of our system. We assume that our input are the linear velocity given to the treadmill and the angular velocity, and this will be labeled by V, and the angular velocity omega given to the turntable. Now, first things that we have to mention before writing this equation is that the motion from below, because of the ball rolling, will be reversed when seen on top. And this picture represents what we see, let's say, from the top camera. You can see the human body is human user is represented by a head which is brown and a body which is green, and it has some absolute location x and y with respect to a set of fixed axes, x0 and y0, while there's another frame with axes xt and yt which is attached to the treadmill. So the treadmill main axis, the one in which we can impose a velocity, will be the xt axis, while yt will be the normal one. The last frame that we may need is a frame which is attached with the human. The human in this case, as I said, is not moving, so it's standing still, and its main axis along the sagittal direction is characterized by an x-axis with a w as subscript. So when the turntable is initially turned on, the xt axis will align with the x0 axis. Now, if we are giving an angular velocity to the turntable, the treadmill will rotate, so the xt axis will rotate with respect to x0, and this angular position will be characterized by a variable which we call theta. So, in a generic instant, the user is placed in a point which is xy with respect to the absolute frame 0, and it has this orientation. Now, what are the other quantities that appear here in the figure? The second command, omega, is the one that will rotate the treadmill through the turntable, so omega will affect directly the variation of theta. And the last two quantities, capital R and alpha. Capital R is just the distance from the human to the center of the platform, where we have located the origin of all our frames, while the angle alpha is the angle between the main orientation of the treadmill and the segments that connect the origin to the location of the human. Now remember that the human is not moving at all. So we have to write the evolution of this variable, x and y, the position of the walker, theta, the orientation of the turntable, and theta w, the orientation of the walker. Now, when we are rotating with the command omega the treadmill, of course, this will change the orientation, so theta dot will be equal to omega. Now, again, we are considering this from the bottom. Now, on top instead, we have the human, and of course, everything is being considered as a rigid body, so the orientation, the absolute orientation of the human will change in the opposite way. So we can write theta dot w equal minus omega. Now what about the position? When we move the treadmill with a linear velocity v, of course, there will be an opposite velocity in the opposite direction of the human. So x dot and y dot will go in the opposite direction of the applied v, but since v is applied along the xt axis, this xt axis is distributed according to sine and cosine on the y and x coordinates, which are defined in terms of the fixed frame. So we have this first contribution, minus v cosine theta and minus v sin theta to the change of x and y. Similarly, no matter if v is present or not, when we are commanding omega, we will impose a linear velocity to the position of the user, which will increase with this distance from the center, and with this plus y omega and minus x omega, you may easily convince that the signs are correct. And for instance, if the user is placed on with theta equals 0, so it's placed on the x0 axis, it means that its coordinate y is 0 and there is some positive x, then if you apply now an omega, being y equals 0, the x dot will not change, while the y dot will change proportionally to the distance x to the center. And the minus sign is, of course, we consider all counterclockwise quantities positive, but the minus is there because if I'm applying an omega positive, then the linear velocity y dot will be negative in this case because of the presence of the reversing action of the Bowler rays. So these are our equation, not very difficult to derive, but we can make a first consideration. First of all, if we look at this equation, we see that the changes of theta and of theta w are equal and opposite. So if we start with a certain value theta of the orientation of the turntable and with a certain value of theta w of absolute orientation of the user, then from there on, this sum, the sum of these two quantities will remain constant. In fact, if we take the time derivative of theta plus theta w, we will have theta dot minus theta dot w, and from the kinematic equation, this will be omega minus omega, so equal to 0. So this will remain constant, equal to the value assumed at the beginning of our experiment. So there's a holonomic constraint, so directly on the coordinates that we are using for describing the situation, which means that we will not be able to control, no matter what we do with our command v and omega, to control independently theta and theta w. So we can take as controlled variable the one that we are interested into, one of the two. Since we are not really interested in the orientation of the walker, as we said, we will consider theta as the main variable that we keep in the picture, while the control will have as output controlled the two coordinates x and y, because we are interested only in the position of the user. Now, there's another thing that needs to be assessed, and this is why we have called this platform also a non-holonomic platform. Because in fact, by playing around with v and omega, you can really bring x, y, and theta, so the position of the user, and the instantaneous orientation of the treadmill to any value, in particular to 0, 0, 0, if you wish. So there is a kind of controllability of this nonlinear kinematic model, but instantaneously you cannot go everywhere. In fact, you can write or you can detect the presence of a non-integrable differential constraint of the Pfaffian type using the model. So if you write this constraint, sine of theta times x dot minus cosine of theta times y dot minus x cosine theta plus y sine theta times theta dot, and you replace in x dot, y dot, theta dot the three top equation of our kinematic model, you realize that you have an instantaneous zero. So this is a constraint which involves the velocities, so the generalized coordinate derivative x dot, y dot, and theta dot, and which should be satisfied at any time. So if you are able to impose some x dot, y dot, automatically theta dot will follow, and this in an instantaneous way. Of course, by doing maneuver, as we know, in the presence of an holonomic constraint, we still can reach any final configuration x, y, theta. This type of consideration, for those of you who have taken the course of autonomous and mobile robotics, and in particular have derived kinematic models for mobile robots, it's something that you should know already. But in that context, the reasoning is reverse. So you start by imposing some non-holonomic constraint, for instance, due to the fact that the wheels are in pure rolling on the ground, and from there you derive a model which specifies what are the feasible motion for the system. Here this non-holonomic constraint was found a posteriori, but still the situation is pretty much the same, so that whatever control method that you have developed or you may think of for a wheel mobile robot could be applied as well to this situation. Okay. So let's go back for a moment to the presence of this holonomic constraint. So the fact that the orientation of the human plus the orientation of the treadmill remain constant. In particular, this constant is given by the initial values of these two quantities. So in this video, which is a simulation with this environment that we set up on purpose for this type of problems, suppose that the orientation of the blue platform, which represents the treadmill effect, of course we were not able to include here the ball array, but you should imagine that on top of this there's a ball array. So in this configuration, theta times 0 is equal to 0. While the orientation of the humanoid, which is close to the boundary of the platform, is rotated by 90. So if we, and counterclockwise, so we have a sum of theta 0 plus theta w times 0, 0 plus 90 degrees, so we have 90 degrees as a whole. Now the user is not walking, but we actuate now the system in such a way that the platform will bring back the user to the center. Now look carefully what happens to the orientation of the platform while doing so. This is of course obtained by some controller, but we don't care about which controller did this, because this is a situation, a constraint that will be imposed no matter which command we are giving to the platform. So pay attention to the orientation of the platform and to the orientation of the humanoid. The sum at the beginning is 90. Okay, now this is running over and over. So you see that at the end there will be an orientation. The platform has rotated clockwise by minus 45 degrees, while the final orientation, absolute orientation of the walker is now 135 degrees. So if you sum this, you obtain 135 minus 45, again 90 degrees. And this is true not only in the final situation where the user has been brought exactly to the center of the platform, but at any time during the transient. So this is a representation of the fact we did not impose this, but we ran the simulation, and this was the result. So verifying this simple presence of this holonomic constraint, which means eventually that we cannot control both this quantity independently. So we removed from the problem the orientation of the walk. So next step is, in fact, the situation where the walker is in motion. Luckily enough, we can work, in this case, by a principle of superposition. So whatever we will do with the two commands v omega and moving the position of the walker and changing his orientation, and accordingly changing also the orientation of the treadmill, which is below, any intentional motion of the user will be added. Now, if we define the linear intentional velocity, capital VW of the walker, with its component along the inertial frame, so along the x0 and y0 axis, and in addition, the intentional change of orientation of the walker around a normal axis to the plane, so with a scalar capital omega w, this will affect exactly x dot, y dot, and theta dot w, but of course not theta dot. Okay? So if nothing is moving from the platform side, v is 0, omega is 0, and the three terms which are in the red blocks will describe simply the velocity motion, linear and angular, of the user. Now, these are exactly the quantity that we cannot measure. I mean, we can predict or approximate this information, but the only thing that we can measure is, in fact, x and y, and possibly also theta w. Okay? So the position of the absolute position of the user and its orientation if needed. So in controlling x and y, which are in fact our true output, so the quantities that we like to assign a value, a final value, typically 0, so center the user to the platform, this quantity will be affected by the intentional motion, which acts as a disturbance. In fact, an unknown disturbance, because we don't know at a given time which will be the value of these velocities. So our design, control design, should take into account the presence of an unknown disturbance, something that cannot be directly measured and compensated for. But in fact, it's the presence of this disturbance which requires the need of the platform to compensate. If there were no motion, the user starts at the center of the platform, remains there forever. So when it starts moving, the platform will see the actual position reached and at this stage apply some control, and we will see that we will combine a feedback term with a feed-forward term, trying to anticipate the next intentional motion in order to center the user to the platform. So the kinematic model, when the walker is in motion, is simply derived from the previous one. No further consideration are needed. So, before designing the controller, and we will do this in several steps, let's have a look at the general block diagram, with some icons there. So the red block is the walker and the platform, and the intentional motion, in particular the intentional linear velocity of the user, will act as a disturbance and x and y are the position of the worker in the absolute frame, are the quantities that we like to control, so they are the output of our system. They are measured through a vision system, for instance, a camera placed on top of this platform. So from the camera we get, after some processing indeed, an x and y at least. This x and y are compared to some reference value, which in this case are simply 0 and 0, because we would like to bring the user at the center of the platform. Later on we will see that you can imagine also strategy where the reference value are time varying and are placed accordingly according to the actual motion of the user. This relaxation of the simple choice of 0, 0 will be useful in order to exploit at most the size of the platform. This is not really a problem for this small size platform because we consider everything pretty much scaled, but when we go to real human walking on the full-scale platform, we will see that bringing the user right to the center is not always the best choice. Anyway, in this case, we take the center as reference, so we generate an error, x reference minus x, and since x reference is 0, this is simply minus x, and y reference minus y, and again, this error along the y direction is simply minus y. But this is not the whole story, because we try to capture also the disturbance. So we try to build an observer of this missing contribution, and in order to build an observer, this will be in fact a disturbance observer, so not a state observer, so an observer of a quantity for which you don't know the dynamics. This is completely different from the case of having a state observer, and for designing the state observer you typically use the dynamic of the missing, the unmeasurable states, at least. So, for doing this, we take the output x and y, if needed also the theta of the platform. We use the command that we give to the platform, and altogether we try to have an estimate v tilde of w of the intentional velocity. And we will use this estimated intentional velocity, linear velocity, properly manipulated inside the control law, which will finally generate v and omega. So here again we have a part which is generated through a feedback error, or through a feedback of the error, and a part which is generated as a feed forward intended to compensate the unknown disturbance. So this is the overall picture. Now let's start with a situation in which we assume that the user is not walking. So the first video that we have seen, or the second video that we have seen in simulation, bringing back to the center a user. Before doing that, let me make some consideration. So in our model, we have used as coordinates x and y, and then the single angle theta. We have discarded from now on theta w. But indeed, we may have used also a different set of coordinates, which are, in particular, apart from theta, the r and the alpha that we have introduced. R, I remind you, it was the actual distance of the user from the center, so it's the square root of x squared plus y squared, while alpha was the angle between the orientation theta of the treadmill and, let's say, the orientation of the line that connects the position xy of the user to the origin. So arctangent with a sign, so arctangent 2 of yx. So you can replace, in fact, x and y modulo the use of theta with these polar coordinates, r and alpha. And we will see that this is useful to have in order to have a compact result at the end. So the direct transformation is clear, but we can also, so from xy using theta to go to r and alpha. What about the opposite, from r and alpha using theta to go to x and y? Well, this is quite simple. So we can write xt and yt. These are the coordinates of the user, but with respect to the treadmill frame. This treadmill frame is rotated with respect to the inertial frame by an angle theta, so we have a 2x2 planar rotation matrix with cosine theta minus sine theta, sine and cosine of theta as their 4 elements. Now the coordinate xt and yt are simply the projection according to the angle alpha of the distance r of the position of the user to the origin. So they are simply r cosine alpha and r sine alpha. So at this stage we can also pre-multiply this equation by the inverse of the rotation matrix. Remember, the rotation matrix is this is the special orthogonal, it belongs to the special orthogonal group of dimension 2, so it's SO2. So its inverse is its transpose. So if we isolate r cosine alpha, r sine alpha on the right hand side, and we pre-multiply by the transpose of the rotation matrix x and y, we get these two equations. So every time we will encounter x cosine theta plus y sine theta, this can be written as r cosine alpha, and similarly if we find y cosine theta minus x sine theta, we will replace this by r sine theta, sine alpha. So we have written the equation in terms of x dot and y dot. Can we write something similar in terms of r dot and alpha dot? The answer is certainly yes. And the two equations that you see at the bottom are the result of suitable manipulation of things. Before giving the proof of this transformation, notice the following, that in the second equation we have a strange factor 2 coming out. So while omega by itself, or minus omega, is affecting the orientation of the worker theta w directly, there's a minus sign because of the reversal of the Ball array. There's a minus sign also here because alpha is defined on top of the platform, while omega is below the platform. But there's a factor of 2. And this factor of 2 puzzled us for a while until we convince ourselves that changing this angle, which is like changing the theta w, in fact, this change is, the effect of omega is doubled on this variable. And this is because at the same time we are moving the treadmill, we are rotating the treadmill, and at the same time the user is counter-rotating so that this effect is doubled. So this is more intuitive than other, but in fact we can derive this equation by analytic term. And I will try to do this in a very elementary way. I have a piece of paper here. Let me switch to a scene where I'm only here. I hope you will see this, and then you can look at it at home in a more careful way. So let's derive the differential equation for r dot, capital R dot. So we start with this information. Let me see if I'm able to show it to you. Okay. So we have r is equal to the square root of x squared plus y squared. And now we take this derivative, and this is the first derivative that we need to write. So this is a square root. The time derivative is, this is x squared plus y squared to the power of 1/2, so we have 1/2. And then we have the power minus 1, so we have the square root at the denominator, so minus 1/2, so we have r below. And then we take the derivative of the argument of the square root. So we have 2 times x dot, we take the derivative with respect to time indeed, plus 2 y dot. Now the factor 2 is being eliminated, 1 over r remains out, and now we have x dot plus y dot. And we use the kinematic model that we have introduced, so in place of x dot we write minus b cosine theta plus y omega. We are considering the case of no motion of the walker. And in place of y dot, we replace v sine theta plus x omega, and with a minus sign in front, because all these quantities were bearing a minus. Now, if you look at this expression in the square bracket, you recognize that the second term in the two parts, this one and this one, will cancel out. So what remains is essentially a minus sign that you factor out, 1 over r, and then v, which you can factor out, x cosine theta plus y sine theta. And this is nothing else than the r cosine alpha that we have just proved in the previous slide. So you simplify the r, and the final equation is r dot equal minus v cosine alpha. Well, pretty much same thing we can do with the second equation. So the equation that describes the evolution of alpha, so alpha dot, when there are commands v and omega. So very similar, we start with this definition. The only thing that we do, because this is in fact a local definition, we replace the arctangent with 4 quadrant, the atan2, with the normal arctangent. And now we write alpha dot, so the time derivative of this quantity with respect to time. The second term will be minus theta dot, and we know already that this is equal to minus omega. But the derivative of the arctangent with respect to a parameter, in this case time, will take this form. Is 1 over 1 plus the square of the argument, so is 1 over 1 plus y over x squared, and then we have to take the derivative of the argument, so of y over x. So we take the derivative of the numerator, y dot, and we leave the denominator untouched, and then we take the derivative of the denominator, so 1 in this product, 1 over x, the derivative is minus 1 over x squared times x dot, and then times y, because the numerator has not been changed. So we have this expression again. We have x dot and y dot, and we will replace here the kinematic model that we derived in the slide. But before doing this, we make a small simplification. So we multiply the denominator by x squared, and the numerator by x squared. The numerator is the quantities in the square bracket. So we have, as a result, 1 over x squared plus y squared. Now we have eliminated the fraction in the second term. And when we multiply by x squared, the square bracket, we have y dot x minus y x dot. While the last part, minus theta dot, has been rewritten as minus omega. And now we replace x dot and y dot, and we obtain the following. Now let me do this, like this, one step at a time. So 1 over x squared plus y squared is nothing else than 1 over r squared, the square of the distance to the origin. And then the x multiply y dot, which is minus v sine of theta minus x omega. And the minus y multiplies the x dot, which is minus b cosine theta plus y omega. And then we have the minus omega left outside. Now, you can see that here we can rearrange things in such a way that we detect, we detect some similar terms. So we can factor in the square bracket the linear velocity v, and we end up with, there are two minus sign in front of the second term, so we have y cosine theta, and then minus x sine theta, all pre-multiplied by v. And then we have a square of x and a square of y, both with a minus sign in front and multiplying omega. So we have again omega x squared plus y squared inside the square bracket. Now again we recognize known terms, which are in fact r sine of alpha at this stage for the first parenthesis, and then again an r square multiplying omega. There's a 1 over r squared outside, so if we simplify, we end up with the final result, which is for the first term v over r times sine alpha, or v times sine alpha over r, and for the second part we have r squared simplified with the outside 1 over r squared, and minus omega remains, and then the minus omega outside we have the famous minus 2 omega. And this is in fact exactly what we get at this point. So with this in mind, let me just move on and start doing some control design. So as I said, we consider first the case of the user standing still. So there's no disturbance, so the linear and angular velocity, intentional velocity of the worker are 0, and we are interested in controlling its position, so x and y only. Now the simple model is still described by nonlinear differential equation. So one possible easy way of controlling such system is try to linearize exactly by feedback this nonlinear differential equation. But in fact, we cannot do this completely, so we achieve a partial feedback linearization, in fact, only of the input-output behavior. For doing this, we have not to do much work, because first of all, we rewrite. We are controlling x and y, so we see their first derivative, how it is affected by the two command v and omega. So in fact, we are just looking at the first two equations of the kinematic model. And these are rewritten in this form: x dot y dot equal a certain matrix, which we will call A, and times the two-dimensional input vector of v and omega. So it's minus v cosine theta plus y omega is the first equation, and the second is minus v sine theta minus omega x equal y dot, exactly what we seen before. Now this matrix is the so-called decoupling matrix, input-output decoupling matrix of the system. For those of you who are familiar with nonlinear control methods, this matrix is built with the relative degree derivative of the output. So the first output has relative degree 1, so after one derivation, x to x dot, at least one input appears, in fact both input appears, and same for the second output y. When you take the first time derivative, you get minus sin theta v minus x omega, so the input at least one, in fact both, appear. Then you organize, you factor out the commands v and omega, and what remains is exactly the decoupling matrix. And now we make a strong assumption here. We assume that this matrix is invertible. And if we compute the determinant, we realize, we find our old friends x cosine theta plus y sine theta as determinant, and we assume that this is different from 0. If this is true, we set as commands v and omega exactly the inverse of this matrix times new velocity commands v1 and v2. You may recognize that this is a standard approach, And the result of this type of commands will be x dot equals simply v1 and y dot equals simply v2. So you see that we have completely decoupled the behavior along the x direction and along the y direction of the position of the user, which is standing still. So with the v1 command we can bring x to 0, and with the v2 command we can bring y to 0, no matter which are their initial value, x of 0 and y of 0 at time 0, okay, at the beginning of our experiment. So the dynamics now of this x and y after the application of this control are linear, and they are decoupled along the two directions, okay? So, with this in mind, we try to stabilize this system. These are simple integrators. We have to stabilize the origin. So the choice that we made is for v1, we choose minus k1x with some positive gain k1, and v2 equal minus k2 of y with some positive gain k2. In this way, the first equation will turn out to be x dot equal minus k1x, and the solution is an exponential with negative power. So starting from some initial value x0, the solution for x in time will be e to the minus k1t x0. So no matter if you start from a positive or negative value of x0, this will converge exponentially to the origin, and the faster, the larger the k1 gain is chosen. But remember that this will affect the command that we're giving to the platform, and if we choose a very large k1, it means that we will give a large velocity to the user is standing still, so typically he will lose balance, and we are violating some perceptual constraint. So k1 is positive but should not be taken too large. Same for y with k2. So we have this type of nice exponential convergence, so we are stabilizing the origin exponentially. From now on, we will make a special choice for the gains k1 and k2. They could be taken positive but arbitrarily. Instead, we will take them equal. So we replace k1 and k2 in the previous equation. So at the bottom of this formula, of this slide, we will have a k1 equal to k2 equal to k, so that if we make a ratio between y and x, or between y0 and x0, at any time, we get exactly the same value, and also of the derivative. So this means that, in fact, if we make this choice, the way in which the position of the user is brought back to the origin will be a straight line. So the worker is standing still somewhere in the platform, typically, possibly close to the boundary of the platform. By applying this controller with an equal gain k in both directions, the user will go straight to the origin. And while doing this, it will also change orientation, because remember, we are applying some omega, and this omega will change the orientation of the worker, as specified by the kinematic model, in particular by the equation that we have discarded from the analysis. Now, if we put everything together, so first the input-output feedback linearization part, and then the stabilization part by this common constant gain k, we end up with this formula, which are written either in terms of the x, y, theta, the first part, or in terms of r and alpha. And you can recognize that the denominator x cosine theta plus y sine theta, which is nothing else than r cosine alpha. And then we have some simplification in the first part, so an r goes away. And for the omega, we have sine and cosine, which generates a tangent of the angle alpha, and the distance r disappears. Now, everything is okay, so we can implement this controller and get the results that we already predicted, so the robot is going, the human is going along a straight line to the center, but we have made an assumption that we should not forget, that we should avoid the singularity of the decoupling matrix. So the singularity of x cosine theta plus 1 sine theta equals 0, or rewritten in the polar coordinate, when the denominator r cosine alpha goes to 0. In particular, when alpha, cosine alpha goes to 0, so for alpha plus or minus pi over 2, and when r is equal to 0, this is a singularity that apparently vanishes in the last expression. In fact, in the expression 1, the red 1, the first equation has r only at the numerator, while in the second equation r has completely disappeared. But when r is equal to 0, so when there is no distance to the origin for the user, then the alpha angle is not defined, so we cannot talk about cosine alpha and tangent of alpha, so we should know what happens in the limit. Okay, so there are these singularities of two kinds. The first one can be easily interpreted, so when alpha is plus or minus pi over 2, it means that the user is along a direction from the origin which is at 90 degrees with the main direction xt of the treadmill. So when the treadmill is moving forward or backward, this will not change the distance of the user, will not decrease, I would say, the distance r of the user. So this control is practically useless in this sense, at least instantaneously. When r is equal to 0, instead, things should be very nice, because we have already reached our goal, because the user is at the center. But still, problem may arise when getting closer to r equals 0. It's like a singularity. The singularity per se, this type of singularity, is not a problem, but getting closer to the singularity, so when we are approaching the origin, so when r becomes small, then we may run into numerical problems. So the two singularities have different meaning. In the first case, we are losing the usefulness of one of the two commands, so that we have less mobility with the platform, with the goal of bringing back the user to the center. In the second case, there's a numerical issue when we're getting closer to the origin. So let's see how we can handle this situation, and in particular these singularities. So let's see. So let's consider first the case where r is different from 0. So we are not yet there, so the user is still off-center. Now, if we take our control law, and we have to handle the singularity alpha equal plus or minus pi over 2, we can multiply our original equation, control equation, by the absolute value of cosine of alpha. Now, if we do so, the resulting controller has no longer this cosine of alpha at the denominator, and the command that we are really implementing are k times r sine of cosine alpha, and we define the sine function in the proper way, so we have a plus 1 when the argument is positive or 0, and a minus 1 value when the argument is negative. And similarly, we used to have the tangent alpha in the omega expression. If we multiply this by cosine of alpha, then we remain only with sine alpha at the numerator, again with the sine of cosine alpha, defined as before. Now, this has in practice eliminated the cosine of alpha at the denominator, so has eliminated the singularity. Of course, there's a price to pay here, namely that the dynamics of our controlled output, so of x dot and y dot, is no longer linear, but it's modulated by the cosine of alpha. Still, you can prove that you have asymptotic stability, not exponential stability, and you can prove this through a Lyapunov-LaSalle analysis. In fact, the remaining part of the slide is exactly saying this, but we will not go into the detail. I will leave you this as a home exercise. The nice thing to see is that we can define a Lyapunov function which is non-negative and zero only at the desired value. When we look at v dot, we can prove that v dot is less or equal than zero, but then we have to look at the invariant state, so using LaSalle, and we realize that by our choice, when v dot is equal to zero, namely when cosine of alpha is equal to zero, then the command omega is plus or minus k, which means that we will not remain in that state because we are rotating the platform in a positive or negative direction, and therefore alpha will move out of its singular situation. So this allows us to conclude that the system is asymptotically stable with this modification. So we still have decoupled behavior of the two controlled output, but no longer linear. This is why we can only conclude about closed loop asymptotic stability and not exponential stability, which is a stronger property, as you may know. There's another nice property, maybe by this. I don't know if I mentioned this, but under this modification, still the ratio of y dot and x dot is equal to the ratio of y over x, which is equal to the ratio of y0 over x0. So still, the transient behavior of the user with this controller is going straight from the initial position to the origin while being rotated by the controller. So still we preserve this straight line behavior in the transient. Sorry, I went to the wrong direction. Okay. Now, what happens when we are getting closer to r equals 0? So the controller that we have just introduced, even with the modification that eliminates the other singularity at cosine alpha equals 0, will be non-smooth close to the origin when r is going to 0. And this will generate in practice some chattering phenomena. So the idea is very simple. We're trying to smooth this behavior even when r is getting closer to 0. And we do this by multiplying the same modified control law by another factor r, which will end up in having a linear velocity for the treadmill. This is the control law, which is k r squared sine of cosine of alpha, and the r introduced also in the omega expression. So we will have kr sine of alpha, sine of cosine alpha, which can both be rewritten in terms of the original coordinate if you prefer to do so. And same story, asymptotic stability, the system closed loop is still nonlinear at this stage. So you have to use Lyapunov-LaSalle argument, pretty much similar to the previous one, in order to prove asymptotic stability. And if the standing worker is subject to this final smooth singularity-free velocity level feedback law, this is the way in which we call this, then the recovery of an initial position to the origin will occur along the straight line connecting the initial position to the origin itself. So, I would like now to conclude this lecture by considering what happens in the presence, so to conclude the control design, what happens when the user is in fact moving. In particular, it has an intentional linear velocity v omega. In fact, the user may also rotate in place or rotate while going in a certain direction, but this effect is not pretty much relevant for our control objective, which is just bringing it back to the center no matter with which orientation. So when we have this intentional velocity, the walker cannot go to the center asymptotically or exponentially that it may be. Why? Because when the error goes to zero, the command vanishes, so the linear speed to the treadmill and the angular speed given to the turntable will go to zero. But if this is the case while the user has an intentional velocity, we will immediately go out of zero. So there will be a conflict situation. The origin is no longer an equilibrium. The simple example is when assume that the walker is going at a constant speed in certain direction. For instance, the straight line with the turntable oriented as its direction of motion. So there will be, it could start from the origin or it could start out of the origin. In any case, after some transient, it will continue to move at that speed v bar. And in order not to be at steady state, so that the position of the user, the absolute position of the user remain at the same point, of course, the treadmill should move at the same speed v bar, and in fact, in the opposite direction. But in order to keep this motion under the previous law, there should be still a distance error, an r bar, which is nothing else than v bar divided by k. So we see that the steady state will be with the user standing still while walking at a constant speed v bar at the distance r bar from the origin. And increasing k, we could reduce this, so we could bring at steady state the user closer and closer to the origin. But of course, this is kind of forbidden because too large k cannot be used. And on the other side, this is a very special situation because the user may stop, change direction, and so on, so we don't know what happens in this transient, if we ever reach a steady state. In fact, this is just to prove that the control system that we set up, when expressed in linear terms, is a type 0 control system. So when there is a constant disturbance and the constant speed of intentional speed of the user is a constant disturbance, then we will have a steady state error. So how do you recover steady state error due to constant disturbances? Well, typically you add an integral action. And this integral action may be added on the linear side of the problem. So if you trace back our design, you first apply the input-output feedback linearization control, you end up with x dot equal v1 and y dot equal to v2. Instead of now closing a loop to the origin minus kx and minus ky, we closed also an integral action. So we factorize out the proportional gain k, and we have another gain a added in front of the integral of the error. And this, in particular in the previous situation, no matter in which direction the user is walking at constant speed, it may be aligned with the treadmill initially or misaligned. Eventually the treadmill will align with the motion of the user and the position will be brought to zero thanks to the presence of the integral term. So the integral term at some point will integrate zero error, so x and y are both zero, and x and y are both zero in the argument of the integral and outside, but the integrator is now has accumulated the proper velocity. So in v1 and v2, and in particular in v and omega, omega will be zero, and v will be equal to the opposite of the constant velocity. So you can achieve perfect placing of a walking user that goes at a constant speed in any direction by the addition of the integral action. However, this is the steady state analysis. What happens in the transient? First of all, we should guarantee that the transient vanishes so that the system is asymptotically stable or exponentially stable in the presence of this modification of the controller. But even then, we may have some problem during the transient. For instance, we may have overshooting. So in order to bring a user which is, let's say, 50 centimeters away, or let's say 1 meter away on the right-hand side from the center of the platform, while trying to bring it at the center of the platform, we may go to the other side by 1.5 meter, which would be a disaster if 1 meter was the maximum allowed displacement from the center because of the size of the platform. So there's no guarantee that the transient has no overshooting. So this idea, the other consideration is that if this is true, in the most simple case of a user walking straight at a constant speed, you may imagine what happens when you integrate an error while the user is changing direction and speed. So what you have accumulated so far into your controller really has no sense in trying to compensate a disturbance which is not constant at steady state and continuously varying. And it may include more damages than benefits. So this is why, after doing some simulation, we decided to discard this type of simple modification, and we decided to introduce a disturbance observer. So this disturbance observer is intended for estimating the intentional linear velocity, what we call capital VW of the walk. And of course, then we will use this for control purposes. So the idea is pretty much simple. We have two coordinates to estimate. So the linear velocity along the x direction and the linear velocity along the y direction, the intentional linear velocity of the user. So VW is a two-dimensional vector, in fact. So we have a dynamics of x dot and y dot. So we make a copy of this dynamics. In fact, we use two additional states, xc of x and xc of y, which are intended to be copies of the dynamics along x and along y, which is affected by the intentional linear velocity v of w. So we make a copy as if this velocity was not there, so minus cosine theta plus y omega and minus v sine theta minus x omega, and all these quantities are coming from what? From the command that we are giving to the platform, v and omega, whatever command we are giving, and from x, y, and theta. Theta is measured by the encoder on the turntable, while x and y is the location of the user as recorded by a camera overlooking the scene. So everything this can be computed. And in place of having in the first equation Vw of x, the true intentional linear velocity along x of the walker, and similarly Vw of y in the equation of xy, since we don't have this quantity, we replace them by this compensating factor, which is again kw, and then x minus the state of this observer, the component x of the state, c of x, and similarly for the y coordinate. And then we claim that exactly this term that we are adding are tilde values, so estimate of the intentional velocity of the user in the x and y absolute direction. So the construction of the observer is pretty straightforward, a copy of the original dynamics, and for the terms that you're missing, some replacement. Now, if you look at the behavior of the estimation error, so the difference between the actual intentional velocity of the worker VW and the estimation VW tilde, then it's easy to see that this error is a filtered version of the intentional velocity error, velocity of the user. And if the user is going at a constant speed, then from the Laplace domain analysis, you have a filter which has a 0 in the origin, so S at the numerator, and the stable pole minus KW at the denominator. So the dynamics of the error, of the estimation error, is stable. And if you have a constant value of VW, the 0 in the origin at steady state will zero the expression of the difference, which means that the V tilde will converge to the actual W. Otherwise, it will be a delayed version, so a filtered version of the intentional velocity. So still you will be close to the actual intentional velocity, but in continuous time, just lagging a little bit behind. Of course, if you increase KW, then you will be closer and closer, but for the same reason this will be, although this is not a direct gain that enters into the control law, still this will give rise to chattering, in particular because of the presence of noise in your commands, of noise into your measurement, and this noise are being amplified into the observer if KW is too large. So I think that we can stop at this point and restart with the next lecture. Thank you for listening.